Welcome to Learn Chemistry Together. This video is about identifying formal charge. Let's break down the concept of formal charge using water and the hydronium ion as our guides. A formal charge is associated with any atom that does not exhibit the appropriate number of valence electrons. To understand how this works, we compare an atom's expected valence electrons with the number of electrons assigned to it in a Lewis structure, calculated using non-bonding dots and shared bonding lines. Example 1. A neutral atom, H2O. The central oxygen atom belongs to group 6A, meaning it has 6 valence electrons. In a neutral water molecule, oxygen is assigned 4 non-bonding electrons from its lone pairs and 2 bonding electrons from its shared lines, totaling 6 assigned electrons. Subtracting these gives a formal charge of 0. 6 minus 6 is equal to 0, meaning the oxygen atom is neutral. Example 2. An atom with a formal charge, H3O+. In the hydronium ion, oxygen still starts with its expected 6 valence electrons. However, it is now assigned 2 non-bonding electrons and 3 bonding lines, shared electrons, resulting in only 5 assigned electrons. Subtracting this gives a formal charge of +1. 6 minus 5 is equal to +1, which creates the positive charge for the ion. Ultimately, keeping track of valence and assigned electrons allows us to accurately map charges across any molecular structure. Next, we're going to break down the step-by-step determination of formal charges using 2 common chemical species, the methoxide ion, CH3O, and the ammonium ion, NH4+. To calculate a formal charge, we use the core formula displayed at the bottom. Formal charge equals group number minus non-bonding electron minus half of bonding electron. Let's walk through this process using 2 examples. Example 1. The methoxide ion, CH3O. Step 1. Determine the appropriate number of valence electrons. By looking at the periodic table, we find that oxygen has 6 valence electrons based on its group number 6A. Step 2. Determine the actual number of valence electrons assigned to each atom. For oxygen, we count 6 non-bonding electrons from its lone pairs and 1 bond, sharing 2 electrons, half of which is 1, giving a total of 7 assigned electrons. 6 plus 1 is equal to 7. Step 3. Assign the formal charge. For oxygen, 6 minus 7 is equal to -1, highlighted by the red box on the oxygen atom. Example 2. The ammonium ion, NH4+. Step 1. Determine the appropriate number of valence electrons. Nitrogen is located in group 5A, meaning it has an appropriate number of 5 valence electrons. Step 2. Determine the actual number of valence electrons assigned in this case. Looking at the central nitrogen atom, it has 0 non-bonding dots and is surrounded by 4 single bonds, sharing 8 bonding electrons total, half of which is 4, yielding 4 assigned electrons. 0 plus 4 is equal to 4. Step 3. Assign the formal charge. Subtracting the assigned electrons from the valence group number gives us 5 minus 4 is equal to +1. This results in a positive formal charge of +1 assigned to the nitrogen-containing system, matching the overall charge of the ammonium ion. By following these 3 clear steps, finding the valence electrons, counting the assigned non-bonding and bonding electrons, and applying the formula, you can accurately determine the formal charge for any atom in a Lewis structure. Now, let's identify formal charges on some structures. Structure A. Aluminum is in group 3A of the periodic table, and it should therefore have 3 valence electrons. In this case, the aluminum atom exhibits 4 valence electrons, 1 for each bond. With 1 extra electron, this aluminum atom will bear a negative charge. Structure B. Nitrogen is in group 5A of the periodic table, and it should therefore have 5 valence electrons. In this case, the nitrogen atom exhibits 6 valence electrons, 1 for each bond and 2 for each lone pair. With 1 extra electron, this nitrogen atom will bear a negative charge. Structure C. Oxygen is in group 6A of the periodic table, and it should therefore have 6 valence electrons. In this case, the oxygen atom exhibits only 5 valence electrons, 1 for each bond and 2 for the lone pair. This oxygen atom is missing an electron, and it therefore bears a positive charge. Structure D. Carbon is in group 4a of the periodic table, and it should therefore have 4 valence electrons. In this case, the carbon atom exhibits 5 valence electrons, 1 for each bond and 2 for the lone pair. With 1 extra electron, this carbon atom will bear a negative charge. Structure E. Carbon is in group 4a of the periodic table, and it should therefore have 4 valence electrons. In this case, the carbon atom exhibits only 3 valence electrons, 1 for each bond. This carbon atom is missing an electron, and it therefore bears a positive charge. Structure F. Oxygen is in group 6a of the periodic table, and it should therefore have 6 valence electrons. In this case, the oxygen atom exhibits only 5 valence electrons, 1 for each bond and 2 for the lone pair. This oxygen atom is missing an electron, and it therefore bears a positive charge. Structure G. 2 of the atoms in this structure exhibit a formal charge because each of these atoms does not exhibit the appropriate number of valence electrons. The aluminum atom, group 3a, should have 3 valence electrons, but it exhibits 4, 1 for each bond. With 1 extra electron, this aluminum atom will bear a negative charge. The neighboring chlorine atom, to the right, should have 7 valence electrons, but it exhibits only 6, 1 for each bond and 2 for each lone pair. It is missing 1 electron, so this chlorine atom will bear a positive charge. Structure H. 2 of the atoms in this structure exhibit a formal charge because each of these atoms does not exhibit the appropriate number of valence electrons. The nitrogen atom, group 5a, should have 5 valence electrons, but it exhibits 4, 1 for each bond. It is missing 1 electron, so this nitrogen atom will bear a positive charge. One of the 2 oxygen atoms, the one on the right, exhibits 7 valence electrons, 1 for the bond and 2 for each lone pair, although it should have only 6. With 1 extra electron, this oxygen atom will bear a negative charge. Structure I. The boron atom in this case exhibits 4 valence electrons, 1 for each bond, although boron, group 3a, should only have 3 valence electrons. With 1 extra electron, this boron atom bears a negative charge. Thank you for watching. Click subscribe for more.